Welcome to this lecture where we're going to talk about representing trees. We're going to talk about basically the primary types of trees and how we represent them. And there are essentially two basic types of trees. There's really just one type of tree, but binary trees are so common that we would and we're going to study a lot about binary trees. So they're, they are kind of their own special type, and we'll spend a lot of time talking about them, but they're not the only type. But of course, binary trees have the property that each node has at most two children. So A has two children here, see I has one child, and J here has no children, right? So a binary tree can have, a node in a binary tree can have 0, 1, or 2 children. But we can also have multi-way or M-way trees. And in this, we can think of it as every node can have up to M pointers, or in a more general sense, it could have any number of children. Um, so you can think of an M-way tree as being limited to having at most M children, or you could think of it as having any number of children. These are sort of two different subtypes, but we'll sort of treat them together. Okay. So here you see A has 3 children, and D has 3 children, H has 2 children, J has 2 children, and so on. Okay. And if you're going to use a tree to model the real world, oftentimes a binary tree just isn't going to cut it. You really would like to have a multi-way tree. Uh, I like to say, for instance, what if you were stuck with binary trees and you wanted to model a file system? Then your file system, the directories, each could have at most 2 items in it. So you have at your root file system, you have 2 directories, and then each of those have 2 directories, and each of those can have up to 2 directories. And so you'd have to go fairly deep into your file system before you could have files at all, um, or any reasonable number of files, and you could only have 2 files per directory. So it would not be very convenient. So you really do want these multi-way trees. Now, how would we represent a multi-way tree? You've probably seen binary trees, so we won't really talk about that too much. But if we wanted to represent a multi-way tree, here's one way that we could do it. And this way, we have a pointer for each child. So we have child 1, child 2, maybe child 3, child 4. However many children we may have, we have that many pointers for each child. Okay, so this is a fixed number of pointers. And if you think about it, a binary tree is exactly like this. It just has 2 pointers, which we often call left and right. Another way of doing this, which is more flexible, is to have a vector of pointers to all the children. And so here we can have a variable number of pointers. So a node could have as many children as we like. So we can make this children vector longer or shorter. And that would be nice. That would be more flexible. And it's not limited to a fixed number of children. But let me show you sort of a surprising alternative to either of these representatives, which is actually much simpler. Okay. Suppose that this was our tree node class. Okay. We could have just 2 pointers, one called child and one called sibling. And could we get away with this for using 2 pointers to represent an M-way or multi-way tree? And it seems strange because we know that if it has 2 pointers, usually that's the left and the right, and so every node can have 2 children. But here, notice there's only one child pointer and there's one sibling pointer, and so we're treating, even though there's still just 2 pointers, we're treating them differently. And if we treat them differently, we can get a different representation. So here's what that would look like. This is what we call a child-sibling tree, and according to the class definition we just gave, A has no sibling. In other words, its sibling pointer is null, but it has one child, which is B. And B has a sibling, which is C. C has a sibling, which is D. And D has a sibling, which is E. And some of those have children themselves, which have siblings and so on, right? So a child sibling tree, we could draw it like this. And you'll notice this is kind of just a binary tree, written slightly askew. But if we think about it differently, if we treat it differently, then conceptually what we have is that all of the children of A are B, C, D, and E, because B is the child, but C, D, and E are siblings of B. So conceptually, B, C, D, and E are all children of A. Okay. Now, again, this is a conceptual representation over here. This is not actually what happens. This is the way we would actually represent the nodes in memory, but this is conceptually how we're thinking about it, okay? So in this way, because every node can have a sibling, we can have as many nodes per child as we like. We just have to continue this sequence on and on and on, right? So there's no limit to the number of children or siblings that a node can have. So here are some advantages and disadvantages, some comments on these different representations. What about the fixed number of pointers? You know, having child 1, child 2, up to child m. There doesn't seem to be much of an advantage to doing it this way. But this is how a binary tree works. So if you're using it for a binary tree, this is simple, straightforward, and I would do it this way. But for using it for more than 2 children, it doesn't seem to make a whole lot of sense. The disadvantage is if you have more than 2 children, it's going to be hard to code this up and have readable code because you're going to be having all these cases where, well, if child 2 exists and if child 3 exists and that sort of thing. So this is not a great representation. I wouldn't recommend it for more than 2 children. If you had a variable number of pointers, in other words, you have a vector of tree node pointers, the advantages are that you don't have a fixed number of pointers like up here. You keep only the pointers that you need because you can add or remove them from the add them to the vector or remove them from the vector. And also you have random pointer access. What do I mean by random pointer access? I mean, if I want to go to the first child, I can go to the vector sub 0. And if I want to go to the fourth child, I can go to the vector sub 3, right? I can just go directly there. I can go to children sub 0, children sub 3. So I have random access to all of those pointers. A disadvantage is that if I wanted to create a child if I have a sequence of children pointers, right? If my children pointers are a vector that looks like this, right? This is my vector children. And I want to insert a new child right there in the middle, I would have to make a space for it by moving all these pointers to the right and then creating a hole right here where I can put a new pointer, right? So inserting into the middle is inefficient, or removing from the middle is inefficient as well. The child sibling pointer representation, some advantages are that this is a very simple implementation. We have exactly 2 pointers always, and we're only keeping the pointers that we need. So we don't have wasted pointers like we do up here, okay? The disadvantage is, of course, no random access. And so if you're traversing through this tree, traversing the siblings is like a linked list. So if we go back up here to our representation, if I want to go from A to E, I can't go directly from A to E. I have to go to B, C, D, E, right? So there is this linked list traversal behavior here. But if the method that you're using the tree is that you're often walking across all the nodes of the tree, then you have to do that anyway. And this is going to be a reasonable representation. So those are different ways of representing general trees that are greater, broader than binary trees that are useful. And you can think about doing these in different ways. I'm sure there are others, but these are sort of the primary ways to think about it.